We will now go through a series of laws regarding gases that can all be derived from the ideal gas law. And each of them is a situation where two of the variables in the ideal gas law are allowed to vary, where the other two are not allowed to vary. And of course, R, the universal gas constant, never varies. It's always a constant. So our first relationship is called Boyle's Law, and it occurs whenever pressure and volume are allowed to vary. And because pressure and volume are the two that are allowed to vary, then that means that the number of moles, N, and T, temperature, are not allowed to vary. And so this whole right side of the ideal gas law is held constant. So a situation, an example of this is shown in this picture where we have a container with a certain volume of gas, and we have a piston on the top of it, and there is a pressure applied to it, and there's therefore a pressure inside of it. And then you change the situation where you apply more pressure, so the pressure inside the container is larger as well, and therefore the volume is smaller. So when pressure increases, volume decreases. All right, so we're going back to the ideal gas law. If you say that this right-hand side of the ideal gas law is constant, then that means also the left side has to be constant. So pressure times volume is a constant. And if pressure times volume is a constant, then that means pressure times volume before is going to equal pressure times volume after any given change to the same number of moles of gas and at the same temperature. So therefore we can say P1 V1 equals P2 V2. So pressure in situation 1 times volume in situation 1 will equal pressure in situation 2 times volume in situation 2. All right, so you need some kind of a container that can vary volume. You need variable volume. And so examples that are frequently used are pistons and cylinders, like we show in this example. Another container that is used is simply a balloon. A balloon has a variable volume. So problems involving Boyle's Law will often be in with pistons and cylinders or with balloons. So let's do an example problem of Boyle's Law. All right, and this one is a balloon. So we'll say a certain balloon, which has a maximum volume of 4 liters, has a volume of 1.7 liters at sea level. When that balloon is carried up Mount Everest, where the pressure is, and do you remember what the pressure is on top of Mount Everest? It's 30 kilopascal. Will the balloon pop? Okay, so we start at 1.7 liters, we carry it up to Mount Everest, we want to know if it's going to exceed 4 liters. So let's do the problem with Boyle's Law relationship. P1 V1 equals P2 V2. Okay, the first situation is down at sea level, where the pressure is, if we want to use the same units, kilopascals, it's about 101.325 kilopascals. The volume at the sea level is 1.7 liters, and then P2 we know is 30 kilopascals, and we don't know V2. So then we can solve for V2. And our kilopascals will cancel, and this is our liters, and we'll get a volume of 5.7 liters. Okay, so does it survive the trip up Mount Everest? No, it does not. It pops, because anything greater than 4 liters will pop. So it pops. All right, notice that when you use this equation, you can use, you don't have to use the pressure units in the universal gas constant, because as long as you use the same one on both sides, the units will cancel. And the same thing with the volume. All right, our next relationship is when we allow volume and temperature to change. And we hold the other constants, the other quantities constant. Okay, so in this case, the number of moles is constant, and the pressure is constant. All right, so what's constant? Pressure, number of moles, and always universal gas constant. All right, so what's an example of this? This is an example where you also need a volume that can change, like a balloon. So you have a balloon at a certain temperature, and you change the temperature, and you see what happens to the balloon. So if you warm up a balloon, it will get larger. All right, so let's solve for Charles's law by putting everything that's constant on one side of the equation. Okay, so what needs to go on one side? We need to have N and R and P. We have to divide by P, and that means that T is going to go over to the other side, and we get V over T. Okay, now we have everything constant on this side of the equation, which means that whatever's on the other side of the equation must also be constant. So the quotient, V over T, must be constant. And that gives us our Charles's law relation, which is V1 over T1 equals V2 over T2. And that is an expression of Charles's law. Now, make sure that when you do a problem in Charles's law, or any other ideal gas law related example, that you have to convert your temperatures to absolute. And you can see why in this example, because you have 0 degrees C, which would be dividing by 0, which you can't do. So be sure to convert to Kelvin. So I will just write that there to remind you. All right. The next law is when you allow pressure and temperature to vary, and everything else is constant, and that is known as Gay-Lussac's law. So again, we're going to let pressure and temperature vary, keep everything else constant. So what's constant? Volume is constant, and R is always constant, and N is constant. All right, so in this case, we don't need a volume that can change. In fact, we want one that won't. We want it to be constant. So we use a solid container, and we're varying temperature and pressure. So one way to do that is take a container full of gas and heat it. And what happens is all the molecules go faster, and therefore they collide with the walls more. And since they collide with the walls more, that's more pressure. All right, again, put everything constant on one side of the equation. We'll put NR over V on one side, and that leaves P over T on the other side. Okay, so this is the constant, this side, which means P over T is a constant, and that gives us P1 over T1 equals P2 over T2. And that is our expression for Gay-Lussac's law. All right, so we've just done 3 laws. We've done every combination of 2 of pressure, volume, and temperature. So when you varied P and V, it's Boyle's law. When you varied V and T, it's Charles's law. And when you vary P and T, it's Gay-Lussac's law. So we haven't varied N at all. We're going to show one example of varying N, and that is known as Avogadro's law. So in Avogadro's law, you vary N and V. All right, so what's an example of varying only N and V? Well, again, if you have a volume that's going to change, you need a balloon or some other volume that can move. So we use a balloon, and a really good example of Avogadro's law is simply blowing up a balloon. As you are blowing into it, you're adding more moles of gas. You're increasing N, and therefore the volume increases. So simple enough. You've known this since you were a little kid, that if you put more air in the balloon, its volume will get larger. All right, so what are we holding constant? We're holding pressure constant, we're holding R always, and we're holding temperature constant. So we again put everything constant on one side, RT over P, which gives us V over N is also constant. So our Avogadro's law is V over N for one situation equals V over N for a second situation. And we'll do an example problem of Avogadro's law. All right, we have a 5-liter balloon of neon gas with 0.965 moles of something at room temperature, of neon gas, sorry, at room temperature and pressure. If the amount of gas is increased to 1.8 moles, what's the new volume? Okay, so let's write down what we know. V1 is 5 liters. V2 we don't know. N1 is 0.965 moles, and N2 is 1.8 moles. All right, so let's set up our equation. V1 over N1 equals V2 over N2. So we get 5 liters over 0.965 moles equals, we don't know V2, and that's over 1.8 moles. You can solve for V2 with a little algebra and get 9.33 liters for the second volume. So there are your 4 laws. We had Boyle's law, Charles's law, Gay-Lussac's law, all of which varied P, V, and T. And then we finally have Avogadro's law, which varies V and N. All of which can be derived from the ideal gas law by holding some things constant and allowing some things to change, 2 at a time.